In this lecture, we'll be discussing the elimination reaction, which means it's a net loss of atoms and a gain of an extra bond. If you'll notice here, cyclohexene, whenever something ends in an ene, it means that you have a double bond, or otherwise known as an unsaturation. So we will be discussing the reaction of cyclohexanol to cyclohexene by an elimination reaction. So as I mentioned earlier, we'll be going over the reaction of cyclohexanol to cyclohexene, and this will be done by an E1 reaction, right? So the first step of the reaction is similar to an SN1 reaction with that we did in a previous lecture of terbutyl alcohol to terbutyl chloride. In both reactions, you protonate a hydroxyl group, which is the alcohol, right? And then water is removed and a carbocation is formed. So one thing to note is why doesn't it undergo a substitution? Well, the main reason is it does, but it actually gets driven towards elimination due to heat and the removal of the water. And in any case, they're substituting water with water, so you end up with a net no reaction because it's the same product, right? So, but basically, in order to get this E1 reaction to work, you need to remove the water so that the elimination occurs. So here you can see the reaction conditions for this E1 reaction in the synthesis of cyclohexanol from cyclohexene. It's what's known as an acid-catalyzed E1 reaction, right? E1 standing for elimination, unimolecular. You can see here your cyclohexanol. You treat it with sulfuric acid and heat. You end up with cyclohexene plus water. Now this water, it would be preferential to be removed. It's one of the reasons why heat is used in order to try to drive off the water with heat to get it to boil off, right? This is one of the reasons that we don't get a substitution product, as you can see. The water doesn't go back to the bond because it is getting boiled off. And one of these techniques used to get water out of your reaction is something called the Dean-Stark trap, which basically uses a solvent that is less dense than water. The water boils up, it condenses, and then it falls down under that solvent so that it can't get out anymore. Typically, this solvent is something with a similar boiling point as water, but it's less dense, something like benzene or toluene, and it'll help eliminate the water completely from the reaction. So here's a little review on elimination reactions, right? You have elimination reactions to make alkenes, which is a carbon-carbon double bond, right? The term elimination describes the fact that a small molecule is being removed from the reactant. In this case, for this reaction, it's going to be water. That's your eliminated product. The 1,2 or a beta elimination indicates that the atoms are lost come from adjacent atoms. You can see here, you would see your alpha carbon here, and your beta hydrogen is the one next to it, right? That's what makes it the beta hydrogen. This is the beta carbon. An elimination reaction forms what's known as a pi bond. So I don't know if you guys have gone through this in class or not, but when you have a first bond between any two atoms, it is what's known as a sigma bond. This is because the orbitals align linearly, right? But then once you form a second or a third bond, those bonds are known as pi bonds, and this is because the orbital overlap is not linear, it is actually vertical, right? You have your orbital here overlapping with an orbital here, and this is what forms a pi bond, which actually looks very different from what was drawn usually from a Lewis structure, right? So a carbon-carbon bond, a single bond, is known as an sp3 bond. This is the hybridization of the orbitals, and it's called an alkane. Carbon-carbon double bond is sp2 hybridized. That means that it's 1/3 s and 2/3 p, the hybrid orbital, and it is known as an alkene. And then a carbon-carbon triple bond is sp hybridized, half s, half p, and it's what's known as an alkyne. And one other thing to note is, as I said earlier, Having the double bond is known as an unsaturation. So in case that ever comes up for you guys. Here you can see an example, right, of what is going on in this reaction. You have here your leaving group, which is this OH and H. You'll notice that this is H2O, right? And it goes over here, and here's your product, right? E1 stands for elimination reaction of one order. So that means that the rate of the reaction is proportional to the concentration of the substrate only. This is to the power of 1, right? That means it's unimolecular. So the rate would be K times the concentration of our Lg, right? It is independent of the concentration of the nucleophile. In this case, the nucleophile is a sulfate, or the sulfate with a hydrogen on it, right? And of course, as I just mentioned, it's a unimolecular reaction of order 1. And you can tell that by this, right? You usually don't put a 1 here, but it is understood, right, that it is a to the power of 1. And this is what's known as an acid-catalyzed dehydration of alcohol to alkene. Dehydration because you're removing this water, right, and you're forming the alkene and water. You can see on this slide the mechanism of how this works. So first off, your hydroxyl group from the alcohol deprotonates this water, which is itself protonated by the sulfuric acid, right? And so you end up forming this ion here. This ion doesn't like to have 3 bonds to it. It's oxygen. So you get your step 2, you remove of the OH, H2O to form this carbocation here. And you have your water as a leaving group. So then the water from the sulfuric acid or even your leaving group, instead of attacking here, it could also attack this hydrogen, right? And you end up forming a double bond here. And so as I said, the water gets driven off. And this is the reason why this doesn't come back to the alkene and attack it, right? Because once this water does its job to form the alkene, it leaves and you never see it again because it got boiled off. And then you end up with your alkene. Of course, there are probably also times when other waters come into this carbocation here as well, but those get eliminated eventually, right, by this same mechanism. And it's just a repeating equilibrium. As you can see here, you have your double arrows. So these things can happen all at once. But at the end, because you're losing water via boiling, you end up with a net formation of the cyclohexene. So here you can see the procedure. One thing to note is that it was modified from the textbook. So you would start off with clamping a 25 milliliter round bottom flask to a ring stand, of course always in the fume hood. You place 5 milliliters of water in the round bottom flask and add 4 milliliters of concentrated sulfuric acid with swirling. So concentrated sulfuric acid is extremely corrosive, right? So be very careful. Do not add water to acid. This is very dangerous. Always add acid to water. The reason for this is because it could jump and you want the acid to have a downward trajectory, right? So that it doesn't bounce up when it falls on the water. Another thing to watch out for is unclamp the flask from the ring stand to swirl it, but hold the flask by the clamp. You don't want to be holding the flask directly. And then reclamp it to the ring stand. The mixing in step 3 is hot, and this is because of the sulfuric acid. Sulfuric acid is very exothermic when it's reacting and it produces heat, so you don't want to touch the flask. Cool the above acid water mixture to 20 to 25 degrees Celsius, and then add 3.2 milliliters of cyclohexanol slowly to the above mixture. Of course, you always want to add boiling chips to these procedures because you don't want the flash boiling, right? Because that can be very dangerous. And you could lose product, of course, as well. And then assemble onto this flaccid distillation apparatus pictured on the next slide. Note that there's an error on your page, on your book, and it refers to a distillation assembly shown in figure 5.10. Figure 5.10 does not picture a distillation assembly, so this is one thing to watch out for when you're reading in your textbook. So here's your azeotropic distillation setup, right? You have here your alcohol thermometer, your adapter, your distillation head, This is what you usually use, your condenser with the water flowing up, as we've discussed before. Vacuum pump adapter to collect your sample in the cooled ice, right? And you have here your Kleisen adapter. This is closed at the top, and this is all connected to your round bottom flask. So, of course, remember all these things should be clamped. This should be clamped as well, but you should have your heating mantle raised up to the round bottom flask. As you can see, this is all very complex, and it's a pain to try to raise all of this up with different clamps versus just lowering this from the whole assembly, right? And this is just another example of this same setup from the previous slide. Of course, that last part isn't all that important. You can just collect it directly from the condenser. You have here again your Kleisen adapter sealed at the top. Of course, 3 boiling chips to make sure that you don't get a superheated fluid. Knocks, what's known as knocking when it boils all fast. And you have here your water in, water out. As I mentioned earlier, your thermometer. And then you have your test tube for collecting on the ice, right, to make sure it's nice and cool. So continuing on with the procedure, after adding your boiling chips, heat the 25 milliliter flask gently to promote distillation, and you continue heating until the residue in the flask just turns black and fumes start evolving. You should have collected about 3 milliliters of distillate in the ice-cooled test tube, and you should have 2 layers. The upper layer should be cyclohexane, and the lower layer water, right? Because organics are usually less dense than water. Not always, but usually, yes. And then with a pasture pipette, remove the lower aqueous layer. And you can see here, drawing, you remove the lower aqueous layer with your pipette. It should be on the bottom, right? And you have your cyclohexane here at the top. So then you would add 1 milliliter of 10% sodium carbonate, this is to neutralize the sulfuric acid. You also want to watch out, you'll probably get foaming. Use the pipette squirting technique. Wash the cyclohexane with aqueous sodium carbonate solution, right? So this solution, you would just wash your sample. And of course here you can see the squirting technique again. Put your pipette down, grab your sodium carbonate and raise it up and then squirt down to make sure your cyclohexane layer gets washed. And of course it's cyclohexane, right? And then you should take about 12 squirts of this to wash it thoroughly. Finally, remove your aqueous sodium carbonate solution and add 1 milliliter of tap water and wash it again with the same procedure as previously mentioned, right? The squirting technique. Again, here's an illustration of how this would be done, right? You remove the basic wash layer, you have your cyclohexane on top, your basic wash layer at the bottom, and then here you have your cyclohexane and your 1 milliliter of water. You would use the squirting technique again with the water, right, to wash it. As I mentioned, you remove the water layer, and then you add half a gram of anhydrous calcium chloride and swirl for about 20 minutes. Of course, you remember from one of the previous lectures, anhydrous calcium chloride is used to remove water, right? And here's the illustration for that. You have your cyclohexane here, again, aqueous layer at the bottom. Remove the aqueous layer with a pipette, and here's your calcium chloride drying your solution. And you want to dry it for 10 to 20 minutes and swirl occasionally to make sure that all the calcium chloride gets in contact with your product here. So this next step is optional. You may or may not need to do this, distilling the sample, right? So you would do a short path distillation to do this. If you undertake the short path distillation, assemble the apparatus shown on the next slide. Transfer your dry cyclohexane to a 25 milliliter round bottom flask. Do not transfer the calcium chloride. We don't want that, right? Distill as specified in the book and the following slide. Do not distill the dryness, right? This is dangerous to do. If you do not distill, then transfer the dry cyclohexane to a clean dry test. And here you can see again, we've seen this before, right? The short path distillation, you have something cooling here to collect your sample. You have your heating well, your round bottom flask, thermometer right here. And that's pretty much it for that. So the next step is to test whether or not you got your product, right? As I mentioned a few slides ago, an unsaturation is a double bond, right? So this is testing for unsaturation. You can use potassium permanganate test. The loss of purple color to form brown precipitate is a unsaturation. So you would put your potassium permanganate in your solution to, or you would put a little bit of the solution into potassium permanganate. So you can see here the reaction, cyclohexene plus potassium permanganate forms manganese oxide and cis-1,2-dihydroxycyclohexane. Note that if the solution is dilute, one may mostly just see the purple KMNO form disappear. So there's another test known as the bromine carbon tetrachloride test. The loss of brown, red or brown bromine color means that you have an unsaturation. So here you can see the reaction. Cyclohexene plus bromine makes a racemic mixture of 1,2-dibromocyclohexane. So the procedures for these tests can be found in your book, right? So I would recommend reading this just for your own knowledge. So here you can see an example of these tests, right? You have your cyclohexene here reacted with bromine and carbon tetrachloride. You form this product here, right? And you can see from here, this is what happens if you have an unsaturation. And then the potassium permanganate test here, you can see reacted with your cyclohexene, you form this dihydroxyl and the manganese oxide. So this is what leads to the change of color here, you can see. So some important things to go over about this procedure for safety. Concentrated sulfuric acid is corrosive, therefore handle it carefully. While the dilution of sulfuric acid always adds acid to the water, never add water to the acid. This can cause severe chemical burns. Wash with copious amounts of water for any skin contact. Note that one doesn't have to often notice a spill on the skin, so be alert to any spills or on your skin or clothing. Any delay in removing the acid can cause much more severe injury. And wash your hands and arms well after this activity. So this produces a volatile compound as sulfur trioxide, which can produce tiny droplets of sulfuric acid on your clothing. So be very, very careful. Exposed clothing will often show small holes after washing. Cyclohexene is flammable and volatile liquid. Take measures to minimize fire hazards and loss by evaporation. This is why you needed the ice, right? Because it can evaporate. Bromine is extremely hazardous. It can cause severe rapid chemical burns and eye damage. It is extremely volatile and can be a severe respiratory irritant. So always make sure to keep it in the hood. Potassium permanganate is a powerful oxidizing agent which can cause a chemical burn and skin discoloration. So you want to watch out for that too. So after you've done your reaction, you've done all the procedures, the workup and everything, you would want to take the weight of your sample, calculate the percent yield, as we've discussed previously. The temperature range of this distillate, so you want to keep track of your temperature. The range should be between 77 and 83 degrees Celsius. And of course, you would also be able to do an IR and an NMR. Usually it's one or the other because they're found in separate rooms. So the labs are usually done simultaneously in two different classrooms right next to each other. Typically, you don't want to have every student from one class go to the other. So you would want to split it, right, with NMR and IR. And that concludes this lecture. As I previously stated, please don't hesitate to ask questions. You can always reach me by my email. You can find it on the syllabus. Please, if you have any doubts with your quiz, get in contact with me. Of course, I can't give you the answer, but I can guide you to the correct answer if you ask. But in any case, this is the end of the lecture. Thank you.